Hello everyone, welcome to Easy Physics again. Now we are going to learn Huygens principle. We are going to learn it to explain the refraction of light. Now let's first start with the nature of waves. This is an overall view of a wave. Think of water waves. As you see, there is oscillation of the medium and the wave is propagating like this. Actually like this. Anyway, okay, this is the overall view of a wave, and this is the side view of the waves, and these are called the crests of the waves, and these are called throws. And this is a crest, this is a throw, and this is a view from above. As you see, these are crests. Okay, likewise these are also crests and these are also crests, but these are throws. Okay, now let's look at another view of the waves, and with this view I am going to define wavefront. Now a wave is propagating, it is propagating like this toward right, and there is a lot of light waves, they are all moving toward the right. And these waves have crests. These are the crests of the waves. When we connect the crests of the waves, we get wavefront. A wavefront is a straight line which is connecting all crests of a set of waves. As you see, they are parallel to each other. This is another wavefront. Why we are learning wavefront? We are going to use them in Huygens principle. So what is Huygens principle? Now assume this is a wavefront and this is another wavefront. I'm not showing the waves but just the wavefronts. Here, as you see, I have deleted everywhere. I am now just showing the wavefronts in this view. Assume we have two wavefronts, this one and that one. Now Huygens principle says that every point on a wavefront, once a wavefront is produced, every point, just here I have shown several points, but assume every point. For simplicity, I will show the several points. The Huygens principle says that every point on a wavefront acts like a new source of wave. The waves are now produced from here, like this. Waves are produced from here. Similarly, every point on this wavefront is now acting like a new source of waves. They are called wavelets. And then once these sources are producing the waves, after some time, a distance of v times t, the waves moves from here to here. If you draw a new line which is tangent to the all of the wavelets, okay, these are all new waves produced by these wavelets, and now you produce a new wavefront. What will be the next, how we can generate the next wavefront? Now assume this is a point. I'm going to choose several points. This is another one and this is another one. So this point is going to act like a source of wave. I'm just randomly drawing three waves. For this one also, I'm going to draw the waves. And once I draw a line tangent to all of these newly produced waves, I am getting a new wavefront. Similarly, each point on this wavefront is going to act like a new source of waves, and then again we are going to produce some waves, and then we are going to draw another tangent line, so the light is going to propagate toward that direction, and these are the wavefronts, and the production of the wavefronts are the explained by the principle of Huygens. Let me repeat. It says that every point on a wavefront acts like a source of like a new source of light, and they are producing new waves, and then sometimes later we draw a straight line which is tangent to all of these new waves, and then a new wavefront is produced. Okay, this was for plane waves. And if we have circular waves, now this is a wavefront. Okay, this is an old wavefront, and this one is a new wavefront. How this new wavefront is produced? Assume every point on this old wave front, every point is acting as a source of light. Okay, think of this one, for example. It produces light, spherical lights. And for example, this one, it also produces waves. For example, this one also produces waves. So once you draw a tangent line to all of these newly produced waves, you are getting the new a new wavefront. So the next one will be, for example, you have waves from this point and waves from this point. Let me draw with another color, it will be better. Waves from this point, also from this point, actually from every point on this line, but for simplicity I am drawing only several of them. New waves are going to be produced, and if you draw a tangent to all of these lines, then you are going to get your new wavefront. I hope it is clear and you have understood. So now let's go to the refraction of light explained with the Huygens principle. Now, as you see here, we have some wavefronts moving from this medium M1 to medium M2. Assume the index of refraction N1 and N2, and let's assume that N2 is bigger than N1. Now it means that the velocity here V1 and velocity here V2, and V1 will be bigger than V2. And these wave fronts are moving toward the boundary between the two. This is the boundary between the two mediums of index of refraction N1 and index of refraction N2. So let's concentrate on only this wavefront. What is the importance of this wavefront? Why this is important? Why? Because when this wavefront, this point of the wavefront reaches the boundary, the other point is still somewhere here. Once this point of the wavefront reaches the boundary, it is going to produce some waves, as the Huygens principle says. Actually, the wavefronts was produced here also, but we are not drawing the wavefronts produced here, and I'm sorry, not wavefronts, the wavelets are produced here, and then we have drawn a straight line tangent to these new waves, and then a new wavefront is produced. These all wavefronts are produced by the principle of Huygens. And now this wavefront and this point now is at the boundary. This point is going to move to the second medium, and then the new waves produced will propagate in the new medium where the velocity is smaller. And after sometimes delta t, when the waves produced by this point, they are going to spread out, and then once they reach to this point, I'm not going to draw them for simplicity. Just see the spread of the new waves from this point. In time delta t, the waves from this point will come to this point, and in the same time the waves from this point are going to reach to this point. When I draw a straight line tangent to the waves, I'm going to get a new wavefront. And now this is another wavefront, this is another wavefront, and then as you see, the waves were moving toward that direction. Let me use another color. The waves were moving in this direction, but now they are moving in this direction. As you see, this was the direction of the wave fronts, and now they are a little bit bent toward the normal. So this is the way we explain the bending of the waves when the light is changing the medium. Can we use the Huygens principle to derive Snell's law? Yes. Let's draw a clear picture here. it will help us better. Now assume we have a boundary between two mediums, index of refraction n1 and index of refraction n2. Now wavefronts are propagating toward the boundary between the two surfaces. These are the wavelengths. Now let's concentrate on this point of this wavefront and this point of the wavefront. This point is now going to enter the second medium, and now assume that n2 is bigger than n1, which means v1 is bigger than v2. Velocity of the light in the second medium will be slower. When the this point is producing the waves, and the waves from this point are going to reach to this point in time delta t, and at the same time the waves from this point are going to move this distance. Relatively, they are going to move a small distance. Why? Because here the velocity is v1 is bigger than the velocity here v2. So if I connect these 2 points, I'm going to get a new wavefront, and now these waves are going to move like this, and this is the new wave fronts. So the light was moving toward that direction, now it is moving toward this direction. Okay, for simplicity, let me clear it. Now this angle is angle of incidence theta 1, and this is the angle of refraction theta 2. And this point, let's say A, this is point B, and this is point C, and this is point D. Okay, let's use the rules of trigonometry. What is sine theta 1? Let me change my color. Sine theta 1 will be equal to, and here is 90 degree, by the way this one is also 90 degree. Sine theta 1 will be AB divided by BC. AB divided by BC. What is sine theta 2, which is the angle of refraction? The sine is CD divided by BC. CD divided by BC. When we divide them side by side, BC and BC are going to cancel each other. Let me write clearly: AB divided by BC times BC divided by CD. Okay, these two cancel each other. Then we got AB over CD. What's AB? The velocity of the light here is v1, and the distance will be v1 times delta t. Similarly, this one will be v2 divided by delta t. Just v2. So this is v1 over delta t divided by v2 over delta t. And finally, we get v1 over v2. Remember from our previous lesson, from our previous video, I explained n is equal to c over v. Or from here you can write v is equal to c over n. Now instead of v1 I can write c over n1 divided by c over n2, which is v2. Then when we cancel c's, we are going to get n2 divided by n1. Now let's write everything from the beginning. Now we have sine theta 1 divided by sine theta 2. Sine theta 1 divided by sine theta 2 will be equal to n2 divided by n1. And Snell's law is usually expressed as sine theta 1 n1 equals sine theta 2 n2. Okay, that's it. Thank you for listening.